Okay, this question is a prove that. It doesn't tell us a method. If we were told what P and Q were, we could probably use proof by induction. Because we don't have a value for P and Q, we can't use that method. And because we've got a factorized denominator, we're expecting to use partial fractions, and therefore it's going to be the method of differences. So our first starting point is to write the fraction as into two fractions. Okay, then we give a common denominator, so we cross multiply them, and that tells us that 1 is a r plus 4 plus b r plus 2, and the denominators will be the same. We let r equals minus 4, gives me 1 equals 0 minus 2b, so b is minus a half, and let r equals minus 2, we get 1 equals 2a plus 0, a is a half. Okay, so now I'm working with the series, I'm doing a sum, r equals 1 to n, that's the same as, I'll leave the half in, sum of, I'm going to take the half out. You could leave the half in, but I'm going to take it out. 1 over r plus 2, take away 1 over r plus 4. Okay, and r equals 1 up to n. So now we're just going to plug in the values and see what happens. So r equals 1, you get a half of a third, take away a fifth. R equals 2, you get half of a quarter, take away a sixth, so no cancelling yet. R equals 3, you get a half of a fifth, take away a seventh, so we have got the cancelling. We knew there'd be a 2 gap because r plus 2 and r plus 4 is a 2 gap, so we can see the cancelling is going to occur. That's going to cancel with that, the sixth will cancel the next one down, and so on. So these two will not cancel, so we'll leave those, and therefore I know the last two won't cancel on the right hand side. So I only really need, I'll do n minus 1 as well, n minus 2, sorry. I get a half, 1 over n plus 2, r equals n minus 1, I get a half, and r equals n 1 over n plus 2. Okay, so because the cancelling occurs diagonally, I know this one cancels with this one, which I can see. This would have cancelled and so on. So I'm left with those two and those two. Okay, so so the sum r, oh, that's the bottom of the page. Sum of r equals 1 to n of our expression equals a half. I've got a third plus a quarter at the top, and I've got minus, depends how you want to do this, 1 over n plus 3 minus 1 over n plus 4. So it's just a matter of simplifying that. I know what I'm aiming for. I've got to have a common denominator of n plus 3, n plus 4 has got to be involved, and I've got to have a common factor of 12 somewhere along the line. So I've got a half. I'm going to make the denominator 12 n plus 3 n plus 4. and then the numerator, third plus a quarter is 7 out of 12, so I get 7 n plus 3 n plus 4. Take away, I've got 12 missing, so it's 12 n plus 4, and take away 12 n plus 3. So therefore the bottom is what I want. It's 24 n plus 3 n plus 4. And we kind of just have to hope the top works out. We know what we're aiming for. So if I expand it, I get 7n squared plus 25n. So finally I'm left with n 7n plus 25 all over 24 n plus 3 n plus 4. Alright, proved, complete, as required, something similar. So I guess I should state P equals 7 and Q equals 25, just to be thorough. Okay, part B, proof that is divisible by 7 for all positive integers n. Now this is a proof by induction question. So we've got f of n equals 2 to the n plus 2, 3 to 2n plus 1. We just test for 1. F of 1 equals 2 cubed plus 3 cubed, which is 35, which is divisible by 7. Okay, so true for n equals 1. Right, so we assume there exists a k such that f of k equals 2 to the k plus 2, 3 to the 2k plus 1 is divisible by 7, equals 7 alpha, and alpha is a member of the natural numbers. Okay, so then f of k plus 1, replace all the k's with a k plus 1, we get 2, k plus 1 plus 2 is k plus 3, 2 lots of k plus 1 plus 1, which is 2k plus 3. Now somehow I've got to write this in terms of f of k, because I know that's a multiple of 7. I'm trying to show this is. So if I take the 2 out, 2 to the k plus 3, plus 3 squared, or 9, times 3 to the 2k plus 1. Now 2 to the k plus 3, sorry, 2k plus 2 that should be, apologies. 2k plus 2 is f of k, take away that, so it's 2 lots of f of k minus 3 lots of 2 to k plus 1 plus 9 lots of 3 to 2k plus 1. So it's 2 f of k minus 2 lots of that plus 9 lots of that, so it's plus 7 times 3 to the 2k plus 1. Replace f of k with 7 alpha, sorry, we get 14 alpha plus 7 times 3 to 2k plus 1. And to be thorough, take the factor of 7 out. So then you put which is divisible by 7. And then at the end you need to conclude in statement, since f of 1 is true, and if f of k is true, then f of k plus 1 is true, then by induction f of n is true for all n greater than or equal to 1, and n is a natural number, or n is an integer. Integer or natural number doesn't matter at that point.